Hello and welcome back. Okay, now we're going to talk about the cross entropy loss. Now, the cross entropy loss uses the negative logarithmic function, and that's why we need to observe how this logarithmic function is and what happens when we use it. So, as you can see, when the input is high, then the output, which is y, is low. Alright, so if you have an input of 1, then your output is 0. If you have an input of 2, then your output is negative. So the more your input increases, the more your output goes lower. Okay. Now, if you have a small, if you have a small input, so let's say somewhere here, let's say somewhere here 0.1, then the output is going to be high. Okay. So if you have a small input somewhere here, for example, between 0.1 and 0.5, then your output is going to be quite high. So it goes linear in this region over here, okay, and then it just gets stably very high. So if your input is 0, then of course your output is extremely high. So for example, here x is 0.2 somewhere here, okay, and the output is 0.6, which is somewhere here, this point over here. So this is the input, which is 0.2, and this is the output, which is 0.6. So first of all, we're going to talk about the binary cross entropy loss, and then we'll proceed to the cross entropy loss. So the binary cross entropy loss is usually used when the output labels have values of 0 or 1. Now, it can also be used when the output labels have values between 0 and 1. And this is the case of autoencoders, for example. In autoencoders, you're learning the network's input. So basically, the output labels have values between 0 and 1. We're going to talk about this in further sections. And it is also widely used when we have only two classes, a 0 or a 1 class. For example, yes or no. When you're trying to predict, let's say, whether a person has diabetes or not. So basically, your prediction is either a yes or a no. You only have two classes. The first class is a yes, the second class is a no. For example, when you're predicting whether this image is a cat or a dog, then you also have two classes. So 0, for example, means dog and 1 means cat. Okay, so whenever you have two classes, then a very good option is to use the binary cross entropy loss. So this is the binary cross entropy loss. This is the formula. So you're going to take your actual prediction, multiply it with the logarithm of your probability, and then 1 minus your actual prediction, you're going to multiply it with the logarithm of 1 minus the probability. Now here y is the actual label. It can be 0 or 1, and it can also be a value between 0 and 1. It depends on your problem. And P is the predicted probability for the class, C is the number of classes, and N is the number of samples. Don't worry much if you don't understand, because in the next few slides we're going to break this up and we're going to show you some examples in order to make sure that you comprehend this equation very well. So first of all, let's look at the case when we only have two classes. Okay, either a 1 or a 0 class. So this is usually the case. Here you can see an example. This is a feed-forward network, and you can only see one output neuron. Basically, we don't really need to use two output neurons, one for each class. We can only use one output neuron because we can know the probability of the second class from the probability of the first class. So, for example, if this predicts 0.8, that means the second class is just 1 minus 0.8. So we don't actually need two classes or two output neurons in our network. We only need one output neuron, and we can know the probability of the second class from the probability of the predicted class right here. Okay, so if we look at this equation right here, then basically I've just removed the summation over the C because we only have two classes here. So this equation reduces to this right here. I've just removed the summation over the C. So basically for each sample, we're either going to take this term or this term right here. So let's say that the label is 1. So if the label is 1, then yi here is the actual label and it equals to 1. So basically you'll have logarithm of your probability. Now this term cancels out because yi here, remember, is the actual label and it's 1. So 1 minus 1 is just 0. So this term will cancel out and you'll only end up with logarithm of your probability. Okay, and when the label is 0, then this is 0 right here. So this term will cancel out and you'll end up with this term right here. Okay, so if yi is 0, then 1 minus 0 is just 1, and you'll just end up with logarithm 1 minus your probability. So for each sample, it's either this term or this term. Okay, so if the label is 1, then it's negative log of your probability, and if the label is 0, then it's negative log of 1 minus your probability. So this is some very simple Python code. Y hat here is the actual prediction. So if y hat equals to 1, then it's negative log y, and if it's 0, then it's negative log 1 minus y. So for each sample, we're either going to take this term or this term. And at the end, we sum over all the samples and then just take the average. So we're going to divide it by n. So this is the case when we have two classes, a 1 or a 0. Okay, for example, cat or dog, yes or no. Whenever you have two classes, then one very good option is to use the binary cross-entropy loss. Now let's talk in the case of multi-label classification. So in multi-label classification, more than one class is correct for the same input. So for example, for this input, we have the first and fourth class as correct classes. Okay, so this is the first class is 1 and the fourth class is also 1. Okay, so we have two correct classes for each sample. So if we take this equation of the binary cross entropy, now for simplicity, we're just going to consider that n equals to 1. So what we're going to do is sum over all the classes. So basically, it's just exactly this equation. We've just removed the summation over n because we just considered that n equals 1 for simplicity. So we'll end up with this equation right here. So what we're going to do is just sum over all the classes. So the correct probability here is 1 for the first class. So 1 times logarithm of your probability. Probability is 0.6. So logarithm of 0.6 plus logarithm of the second class. So the second class is actually the wrong class, which is 0. So we're going to use this term right here. Okay, so 1 minus 0 is just 1, and you'll end up with logarithm 1 minus your probability. So logarithm 1 minus 0.9. Same exact thing for the third class, logarithm 1 minus 0.2. And for the fourth class, you have an output label of 1. So we're going to take the first term, so logarithm of 0.8. So we're going to sum all of these up, and we'll end up with the binary cross-entropy loss. And here, remember, we've only considered n equals to 1. So one important thing to notice here is that the outputs are ran through a sigmoid activation function. Okay, so your outputs need to be in the range between 0 and 1. So we run it through a sigmoid activation function, and then we compute the loss. Now, an example of multi-label classification is when you want to predict some attributes of the image, some instances. Okay, so this is sometimes called multiple instance learning. So here, for example, we have this image, and we predicted the attributes of this image. So beach, dog, brown, sitting, laying, people, walking. So in this case, more than one class belongs to an image. More than one label belongs to an image. And this is the case of multi-label classification. Now let's talk about how the binary cross-entropy works, and let's analyze the equation. So let's just for simplicity consider n as 1. So the first case, if the label is 1 and the prediction is 0.1. So obviously that loss should be high because your actual output is 1, but your network predicted is 0.1. So what happens here is only this term is valid because the label is 1. So this term becomes, we have a negative here. So negative logarithmic of your probability. So negative logarithm 0.1. And you get, of course, a high loss. Now, if the label is 1 and the prediction is almost 1, so somewhere like 0.9, then again, this is your BCE loss, negative y logarithmic of your prediction, and you get a low loss. So the loss is low. Now, if the label is 0, and the prediction is 0.9, obviously you should get a high loss, of course. Okay, so this when the label is 0, then this term here becomes your binary cross entropy loss. So -1 minus y logarithm 1 minus prediction. Okay, and you get the loss of negative log, and 1 minus your prediction is 0.9, so negative log 0.1, and you get a high loss. And if your label is 0 and the prediction is 0.1, so obviously close numbers, so the loss should be low. So negative 1 minus y log 1 minus p, again negative log 1 minus 0.1, which is your prediction, and you get a negative log 0.9, so your loss is low. Okay, so for example, if you want to observe this from the graph, negative log 0.9 and 0.9 is somewhere here. Okay, so the loss, the output, which is here, is low. Okay, so loss is low. And now if we realize what's happening, that okay, if the label is 1 and the prediction is 0.1, then this is minimized, and of course when the label is 0 and the prediction is 0.9, this is minimized. So when you minimize this, this is what you should reach. This is the ideal case. So your label is 1 here, you get a high loss, you minimize that loss until your loss is very low, ideally 0. So when your loss is low, then this probability is 1, which is what our expected label is. And same exact thing, okay, for the when the label is 0 and you have a very high prediction, which is close to 1, then this loss is minimized, and when this is minimized enough, then the ideal case is 0. Okay, so once you have 0, so then you get an ideal loss, sorry, a label of 0. So your loss is minimized. So when your loss becomes 0, and this is of course an ideal case, when it becomes 0, then your label is 0. So that's how you can understand it. So your label is 0 and your prediction is 0. Okay, and here your label is 1 and your prediction is 1. Okay, so here the prediction is 1, and if you plug 1 here, you get 0 loss. So this is just the opposite way, and when your prediction is 0, you plug it here, you get a loss of 0. And therefore your predictions become 1 and 0, which are the expected ones. So 1, the expected one is 1, 0, the expected one is 0. That's how the binary cross entropy works. Alright, next video we'll talk about the cross entropy. Thank you very much, and I'll see you next time.